Welcome to the post-pre-class video.
Okay.
It's 2 in 1 today.
Oh, nice.
Yeah, exactly. And so in class we did some problems on calculating percent ionization and pHs of different acid-base solutions. And the next class period we're going to be talking about the pH of salt solutions, the acid-base properties of salts. So I thought I would kind of combine those two together.
Great idea.
Yeah. And so I'm just going to do an example, and hopefully this illustrates a couple different points that are important. And the question is, what is the pH of a 0.35 molar sodium hydrosulfide? Right? I was going to write solution, but I didn't have space.
Nash.
Yeah, Nash. Okay, well, does that look like an acid or base? It looks like an ionic compound to me.
Yeah, right? It does.
So one of the things we're going to learn about is that salt solutions can be either acids or bases.
Interesting.
Right? And the thing you got to do is recognize for a salt, the first thing to do is to split it up into its ions, because the ions are going to behave separately.
Cool.
Right? So I look at that and I say, oh, well, I recognize sodium. I'm going to write that down as sodium plus.
There's one of your ions.
Right. And I'll even put a little AQ behind that.
That's helpful.
And I know that I have 0.35 molar. What about the other part of that?
Well, because we know that sodium is 1 plus, we can assume that it's going to form an anion with a charge of -1.
Yeah. And I'm going to put that AQ. Okay, so how did we know not to split the sulfur and the hydrogen apart?
Because that would be strange.
It would be strange, and it would be asking a little bit much of you guys, right? We're only going to give you ionic compounds that split into 2 parts.
Okay, that's good.
And you knew the sodium, that's an ion, so the rest of it. And what do we call that? We call that a polyatomic ion. Okay, so we have our 2 parts of the salt. And what do we know about the chemistry of sodium? What does sodium do in reactions? In almost every reaction you've ever seen sodium in, what's its role?
It is searching.
It's searching, it's watching.
It's like playing charades.
It's sitting in the audience, spectating. Right?
Ah.
So it's going to be important to recognize what are spectator ions, because spectator ions aren't acid-base active. Sodium, it's a spectator ion, and so for the rest of the problem, I'm going to ignore it.
That's good.
Yeah. How are we going to recognize spectators? Well, you have to kind of have in your head an idea of what things tend to be spectators. Sodium, potassium, anything on the solubility chart that said that it was soluble, nitrate. We actually give you a rule in the next activity, and so make sure to look out for that. Spectators are, it simplifies, cuts the problem in half.
There you go.
Okay, another thing is that anions tend to be bases.
Ah.
Right, so I've eliminated the cation, so I know this is probably going to act as a base.
Right, because is it because it's negative? And
Exactly.
It attracts that positive proton?
Exactly. So I've now figured out that this is actually a base problem. And so I'm going to write out, the next step is to write out the balanced equation.
Okay.
HS minus AQ. And for a base, if there's no hydroxide in it, we have to react this with water in a base hydrolysis. If there is hydroxide in it, we just have hydroxide. Yeah. Right? So it reacts with water, H2O liquid, and it pulls off one of the hydrogens and makes OH minus. Right? So here we have our reaction. Okay, now I can write in the concentration, right, by 0.35 molar. And what else do I start with? 0
Yes.
and 0. Right? I'm going to set up.
Starting on ice?
Yeah, an ice table. Right? I'm going to go with water because it's pure liquid.
Right.
And for my change, minus x plus x plus x. For my equilibrium, 0.35 minus x, x and x. Oh, this is old hat now.
You guys are pros.
Okay. Well, now I want to write out my equilibrium expression.
Okay.
So I write K equals the products over reactants. And what do I want to put down here next to the K?
This is KB.
It's KB.
That's very important because
Yep.
it's a base.
It's a base. I've written the base hydrolysis, so this is a KB. And so I can put in my values into the equilibrium expression. X times x, 0.35 minus x on the bottom. And what do I do now? I have two unknowns.
Huh. I wonder if there's some way you could solve for KB or get a KB value.
Yeah. We need a KB value, right? And so you have that handout, and the key is going to be, what column do I look in, right? There's a column for the name, a column for the acid, a column for base, and a column for the Ka.
Wow, that's a lot of columns.
Right? There's no column for Kb.
But there's a value for this, for shish.
For shish. Right, so I'm looking in the base column. This appears in the base column. It gives me the Ka for its conjugate acid.
Right.
Okay?
So let's move over.
So we're going to have to move over to the other. All right, so we looked in the table, and we got our Ka, and the acid, the conjugate acid, is H2S. And the Ka, 8.9 times 10 to the minus 8. And we know that if we know the Ka of something, we can calculate the Kb of its conjugate base.
And we do that using the magical constant for water.
Yep, the Kw. So Kb equals Kw over Ka. 10 to the minus 14 is always the value for Kw at normal temperatures. And this is the Ka value from that table, and so we get the value for Kb that we can now use.
Great.
Right? So all I did was took that value of Kb and put it into our equilibrium expression. And I'm going to assume that since this is a really small number, the change is going to be pretty much 0.
Oh yeah.
Okay, so that goes to 0, and your old hands at doing this, you solve that, and you figure out that x equals 1.98 times 10 to the minus 4. And that's the concentration of hydroxide, because that goes back to our balanced equation.
Okay.
Okay? So there are a couple of ways. The question is, what's the pH? And there are a couple of ways to do that, right?
So when we had that that 4 with the arrows, right? So you could go from concentration of OH to concentration of H.
Yep.
Right? Or the way that Dr. Godes did it.
Yeah. I just took the negative log of this number and calculated POH is 3.7. And that's easy enough because pH and POH add up to 14, and so 14 minus this gives a pH of 10.3. And one last thing about this pH is we notice it's 10.3.
Right.
Well, something that we really didn't emphasize in class enough, I think, is that neutral pH is 7.
Right.
Anything less than that is acidic, anything more than that is basic. And so that's a double check. I decided at the beginning of the problem, it's a basic solution, and so at the end, the pH better be greater than 7, and it is.
Right.
It's not a lot greater, but it's somewhat greater.
It's more basic than I thought it would be.
Yeah.
Okay.
Okay?
So a lot of things that went into that problem.
Yeah, a lot of different skills. That's pretty much as complicated as they get, I think.
Great, so if you can do this, you'll do well.
You're golden.
There you go. All right.
Okay, so see you in class.